Okay, so next let me tell you about some special types of elements in a ring. So one type we've already seen. So definition, A in R is called a unit in R if there exists B in R such that A times B equals 1. Remember, I'm assuming that my ring is commutative and has a unit element, a 1. So a unit element for the ring should not be confused with an element being a unit, which is what this is. And then there's a nice connection here between group theory and ring theory, which is that if R is a ring, the units in R form a group called group of units, and written R cross. Okay? And a nice example of this is, again, we go back to our ring Z mod NZ. And maybe some of you have seen the notation Z mod NZ cross. For those residue classes mod n, represented by integers a that are relatively prime to n. And now we see that this is exactly because this agrees with what I've written for a general ring R. So Z mod NZ cross, this is the set of A in Z mod NZ such that A is relatively prime to n, right? Because we know by the Euclidean algorithm that if A is relatively prime to n, then we can find x and y such that ax plus ny is equal to 1, which modulo n is finding an inverse for A, right? If I have ax plus ny equals 1, then this means that ax is congruent to 1 mod n. So this is Euclidean algorithm. And the other direction, that if they're not relatively prime, there's no inverse. We already discussed that in a previous lecture, and it's easier to see. Okay? So these are the units. So units are kind of like good elements. Now there are some bad elements too. So definition, a zero divisor in R is x in R such that x is non-zero and there exists y non-zero y in R with x times y equal to 0. So this might be counterintuitive. In many of the rings that you are used to, there do not exist zero divisors. So you have two non-zero elements and their product is 0. But for an example, we can go back to our Z mod NZ with n naught prime. So in Z mod 10Z, 2 times 5 is equal to 0. So 2 and 5 are both zero divisors. In R. Okay, so as you can see, this is kind of an unfortunate situation when it happens. So we give a name to all those rings when this never happens. So an integral domain is a ring R with no zero divisors, i.e. AB equals 0 in R implies A equals 0 or B equals 0 for all A, B in R. Okay. So most of the rings, other than Z mod NZ, all of the rings that we will look at will be integral domains. But I do want to mention that there is another type of bad element that is even worse than zero divisors. So an element X in a ring R, R is no longer assumed to be an integral domain, is nilpotent if there exists n, a positive integer such that x to the n is equal to 0. Okay, but this can still happen in our rings Z mod NZ. So for example, in Z mod 25Z, 5 squared, this is 25, which is 0. So 5 is nilpotent in Z mod 25Z. Now, note that nilpotent elements do not arise in an integral domain except for 0. 0 is allowed as a nilpotent element. I didn't say x not equal to 0, so if R is an integral domain and x is not equal to 0, x in R, then x is not nilpotent. Okay, so another way to say that is the set of nilpotent elements in R just consists of the 0 element. In general, the set of nilpotent elements forms an ideal, and what we are saying is that in an integral domain, the ideal of nilpotent elements is the 0 ideal. Okay. Okay, so finally, the last type of element I want to tell you is a bit more specific to the case of integral domains. So zero divisor and nilpotent elements, these are things that are a bit more exotic that can happen in general rings. Now we want to focus on what happens in integral domains. So let R be an integral domain. So definition, let x in R be non-zero and not a unit. So, i.e., x is not in R cross. That was our notation for the group of units, and x is also not equal to 0. Okay? Then we say x is irreducible so we want this to be modeled on, in some way, on what we know about prime numbers in the ring of integers, that they are irreducible. You cannot break them down into smaller integers by multiplication, then we say x is irreducible if given x equals y times z, given an equation like this, where we seem to have been factoring it, then either y is a unit or z is a unit. Okay? So this is just like saying that if you have a prime number, so example, in z, n is irreducible if and only if n is prime. Okay? So if I have n equal to ab, then I know that, so if n is prime and n is equal to ab, then I know that a is equal to plus or minus 1, or b is equal to plus or minus 1. Here I have n, a, and b, all three of them integers. And plus or minus 1, this is exactly the group of units in the ring of integers. Okay? Now you might ask, why did we call it irreducible and we didn't just call it prime? Because in the integers we call them prime, not irreducible. And the point is that there are actually two ways that we can generalize the notion of a prime number. So one is what I just wrote down. The other property of a prime that we have is recall Euclid's lemma. It says if p is prime, this implies that p, well, assume p is prime. If I have p divides ab, this implies that p divides a or p divides b. Okay? So this is another fundamental property of prime numbers, that we can try to generalize this to elements in a ring. And we will do this as soon as we say what a prime ideal is. So an element will be called prime if the ideal that it generates is a prime ideal. And then the point is that in general rings, irreducible and prime are two different things. But we will see the relationship between them.